So for this video, I'm going to be talking about how we're actually going to start filling these electrons into our orbitals in order to get to the correct electron configuration that we're actually going to start be exploring here later, or for the rest of this chapter, basically. And so the first thing I want to kind of point out is when you're looking at this order of orbitals, I guarantee you the first time you glance at it, it's going to be slightly confusing unless you actually know kind of what you're looking at and how they came up with all these levels here. And so the very, very lowest energy orbital that we're going to be starting off with every single time is going to be the 1s orbital. And so as you can kind of see towards the bottom of the screen here, this 1s orbital, there's one of them. And so the reason for that actually goes back to all the information that you should have at least comprehended somewhat from chapter 7. And so in this case, we are looking at n equals 1. And we know that because that number right there is the energy level we're talking about. For anything up above that that has a 2 in front of it, this whole grouping right here belongs in your n equals 2. As we go up another energy level, everything that has a 3 in front of it, these three, or this 3s, these 3p's, and these 3d's here all belong in the n equals 3 orbital. And so we kind of go through and start talking about these when we kind of start, sorry, not orbitals, energy levels. And so we kind of go through and start filling these things in. There's a few rules that you have to follow. But before I get into these rules, I'm going to actually explain why there's these certain numbers of these certain orbitals and these certain directions and everything else kind of going on here. So the first one, that 1s, as I kind of stated, this 1s exists in your n equals 1 energy state or energy level. And so whenever n equals 1, following the rules and the restrictions that we set on our L's and our M sub L's, if your n equals 1, the only option you have for your L is going to be 0. Remember, your L's go from 0 all the way up to n minus 1. And so for this particular issue, or for this particular level, your n equals 1 is always going to have an L equal to 0, and that's it. That's all you have available. And so if you recall, your L equals 0 represents an s orbital. And so in addition to that, when your L is equal to 0, your M sub L is also the only option you have is 0. And all that M sub L is really telling you is that you have only one orientation of your s orbital. The s orbitals are like a sphere shape, and as I've kind of stated before, you can only rotate a sphere one way and it still look like a sphere. There's no other unique directions you can place this thing into. And so for your n equals 1, your L equals 0, which represents an s orbital, and your M sub L represents, or is 0, which represents the fact that there is only one orientation that you can place this s orbital in for it to be unique. Hence why all of this here is one line represented by a 1s. And so again, there's only one line because your M sub L is equal to 0, and there's only one way you can actually fit this in. So all this just to say that in your n equals 1, you only have the option of one orbital, and that orbital is an s orbital. That's all you can access. But if we move up for our n equals 1 to n equals 2, now we have kind of a new kind of scheme going on here. So for your n equals 2, or whenever you're in your second energy level, your L can equal 0 and 1. And recall from the previous chapter, your 0 represents an s orbital, while your 1 represents a p orbital. And so whenever your L is equal to 0, you still only have one option, and that's going to be the s orbital, which is only one way you can orientate these things. And so for your 2s, notice you only have one line to access for your 2s. But whenever your L is equal to 1, now you have three options. You have your M sub L equal to -1, a 0, and a +1. And because of that, you have three orientations in which your p orbitals can be shaped here. And so again, this is all arbitrary numbers. I'm not saying this is -1, that's 0, and that's 1. All I'm really saying is there's three numbers here, so we have to have three lines. And so we recall that the p orbitals, they can go up and down like this, they can go side to side like this, and I can't really illustrate, but they can kind of come in and out of the screen as well. And so these dumbbell shapes can be orientated three different ways around the XYZ axis, hence why you have three 2p orbitals. Additionally, you should recognize the fact, and again, energy is going up here. And so when you look at these, this 2p and that 2p and that 2p are pretty much indistinguishable from one another because they're all going to have the same energy level. When we start looking at these more complicated issues of what P's and D's and everything else, you just have to understand that whenever you talk about a 2p, you normally can't say, I want the 2p that's standing up, or I want the 2p that's laying down. Whenever you fill in these electrons, they go into a 2p orbital. And again, only the electron really knows which one it ended up in. And so these three lines here are always going to be at the same energy level because they are what they're like, are indiscriminate of each, or sorry, unrecognizable from each other here. And so the next step is when we go from our n equals 2 to n equals 3. And so additionally, your n equals 3 has a 3s orbital just like your 2s orbital and just like the 1s orbital. Your 3p has 3p or 3p's just the same way that your 2 had 2 or 3 2p's. But in addition to this, we have our L equals 0, we have our L equals 1, but for n equals 3, we also have an L equal to 2. And as you can kind of see here, your L equals 2 is represented by the d orbitals. And so in these cases, as you have L equal to 2, your m sub L is going to equal negative 2, negative 1, 0, positive 1, and positive 2. Remember, all these exist. You can't just choose one of them from this grouping here. And so in this instance, that's why there are 5 of your 3d orbitals. And so I'll talk about the 4p's here in just a little bit, or 4s, or n equals 4 in like a couple more videos. And so these 3 guys down here, or I guess 3 rules down here, represent how you have to fill these electrons in. And so the first rule kind of makes them a little bit of sense, is Aufbau's rule states that you have to fill in these electrons in the lowest energy levels first before you can start moving up. And so the way that I kind of describe this is, say that you just went to the grocery store, and if they have all the food that you need and everything nowadays, but say you go to the grocery store and you come home and you have all your groceries, you go into your pantry and there is a lot of empty space on the lower shelf that you can have easy access to, and there's also some space on the shelf that is all the way on top that you have to stand on your tippy toes in order to put stuff on there. Most likely you should kind of, again, makes more common sense to fill in your bags and fill in your groceries on that lower level before you have to start putting more energy into standing on your tippy toes and jumping up and down to fill the top shelf of that. And so here you're always going to fill in the lowest energy level first. And lo and behold, if you look at this diagram here, 1s is always going to be your lowest energy level. And so you always start off with your 1s, then you go to your 2s, then you go to your 2p, then your 3s, then your 3p, so on and so forth. The next rule we have to talk about is Pauli exclusion's principle. And so Pauli's exclusion principle states the fact that 2 electrons can have the same 3 quantum numbers, meaning the fact they can have the same m, they can have the same n, same L, same m sub L, but that 4th quantum number, or the spin quantum number, has to be different. And so this is basically stating the fact that you cannot have 2 electrons existing in the same exact spot at the same exact time. This makes some sense because if you've ever tried to walk through a wall, you realize it's kind of difficult because the wall is made up of atoms that have electrons. You are made up of atoms that have electrons, and these cannot exist in the same time at the same place in any dimension. And so the Pauli's exclusion principle narrows down that you can only put 2 electrons per orbital, and they must have opposite spins. And by that I mean you can have a 2 electrons in the 2s. You can have an n equals 2. You can have an L equals excuse me, an L equals 0, and you can have an m sub L equal to 0 for 2 electrons. But the last quantum number, that spin quantum number, has to be a positive half for one of those electrons and a negative half for the other electron. And the same exact deal applies for every single one of these lines. You can have a positive and a negative, and both of them have to, again, have the same first three quantum numbers. The last one has to be opposite of each other. And the last rule we have to kind of talk about is Hund's rule. And so Hund's rule states the fact that you have to fill in every single level that has equal energies with at least one electron before you can start doubling up. And so as I mentioned with the exclusion principle, only 2 electrons can exist in each one of these orbitals. But you can't just start throwing 2 electrons in every one of these orbitals without following Hund's rule first. And so what I mean by that is if we have something like 2s2, 2p4. And so what I mean by that is there's 2 electrons in your 2s, and there's 4 electrons in all of your 2p's. And so the way you would set this up is you would actually put 1 electron in this 2p, then a second electron in this 2p, and a third electron in that 2p before you can start doubling up on these things. And so what I mean is you can't have 2 electrons here and 2 electrons there and no electrons in this last p orbital. Because they're all equal energies, you have to make sure that you spread out all of your electrons equally before you start doubling up on them. And so the way that I can kind of describe this is, say that you go to a hotel with you and your best friend in the whole entire world, but you enter the hotel room and there are 2 beds. And so it would make sense for the both of you to go and lay in your own individual bed first before you just have 2 people in one bed and 0 people in the other bed. And again, this is just kind of the common idea that makes sense whenever you start talking about these energy levels. They need to be spread out completely before you start making these things a little bit more complicated. And so one additional thing I want to kind of point out when we start talking about these is every single one of these s orbitals, this 2s orbital, this 3s orbital, that 4s, that 5s, these are all the same shape. The only difference between the 1s and the 2s and the 3s is that the 3s orbital is going to be bigger. The 2s orbital is going to be in between the size of your 3s and your 3s and 1s. And the 1s orbital is going to be relatively small compared to everything else in this slide here. And so when we kind of go through and talk about these, the way I usually describe the s orbitals is think of, well, some of you have known them as the everlasting gobstoppers or even just a jawbreaker. And so when we take a jawbreaker and you have, again, these layers, and so on the inner core of that, you have that soft, chewy little portion, and we'll call that the nucleus. And so the first layer around the nucleus is going to be your 1s. The second layer around that is going to be your 2s. The third layer is going to be around, it's going to be the 3s. But note here again, I'm not changing the shape, I'm not doing anything, I'm just having my gobstopper starting off, and then you dip it, it has a layer, you dip it again, has a second layer, dip it again, has a third layer, so on and so forth. And so you can kind of think about these in just overlapping layers. And so the 5s contains everything that is in the 4s and everything that's in 3s and 2s and so 1s and so on. And so the last thing I have to kind of point out here about this crazy looking diagram is you should kind of notice when you look at this, the 1s going to the 2s, there's a bigger gap there because, as we mentioned, the 1s is a lot closer to the nucleus, and going from n equals 1 to n equals 2 is going to be a much larger energy gap. But as we start moving on here, we have our 2 kind of, again, centralized, it's all kind of separated from the 3s. But once we get into this, if you follow the energy, we fill in the 1s, 2s, 2p, 3s, 3p, but we can't go directly to the 3d. And the reason for that is this 4s is lower in energy than the 3d. And so because of that, we actually have to fill in the 4s first before we fill in the 3d orbital. And so this is going to be kind of, again, slightly confusing when you kind of go and fill these in. Because typically, the way that our brains work, we fill in 1 and then 2, then 3, then 4, then 5, then 6. But unfortunately, because some of these levels split due to shielding and penetration effects, and please look, I have them in my slides, look all those up on your time. But because of the shielding penetration effects, your 4s energy level actually ends up being lower in energy than your 3d orbitals. And because of that, you're going to fill in your 3s, then your 3p, then your 4s, then your 3d, then your 4p, then your 5s, then your 4d. And again, I know this seems really confusing, but there are plenty of hints and I guess shortcuts on how to figure this stuff out.